Welcome back to ECE 220. If you are trying to decipher the announcements, hopefully they're clear. I tried to give you all of the dates that we will no longer when we will not be meeting in class. One of those is a week from tomorrow. Next Wednesday is the day before Thanksgiving break. That's the 27th. Another one is the Friday following exam number 4. Exam number 4 is the week that we return from Thanksgiving, and that's going to be on a Thursday, as always. Our exam will be on the 5th of December, and then we also will not be in class the last day of the semester, the last class day of the semester. Those are the remaining 3 times I'm releasing you from attendance here in the class. You are still responsible for all of your other commitments for class. One of those is homework 12 is due today. The others are your labs. Lab 5 begins today for Group A, and that continues through the rest of the week. And then Group B, tomorrow your lab number 4 is due, and your pre-lab for lab number 5 is due on Saturday. Hopefully all of that is consistent with what I have mentioned in the past and the way that we will progress through the rest of the semester. And right now I'm thinking we might have those last 2 days of the semester that we do meet, the Monday and Tuesday, those may be review for the final exam. Just seeing how far we get. But today we want to be basically in 2 different domains. Maybe not at the same time, but we want to know when we're in one versus the other. When are we in the time domain, and when are we in the frequency domain, and why are we worried about that? Well, we're trying to simplify our analysis by saying, you know what, let's just wait until the transient is finished, then everything will be shaking at the same frequency. We're dealing with linear circuits, so everything has the same frequency. It just may not be aligned peak to peak or valley to valley, and the amplitudes may be different. And that's what we want to keep track of. So if we can keep track of amplitudes and angles, that's the time relationship, the phase shift, then we can, if somebody wants us to go back into the time domain, we can give them the time domain expression relative to whatever we're interested in, which might be a source voltage, it might be a source current, it might be voltages and currents on these different RLC elements in our circuit. That's what we want to get comfortable with, and that means that we will be playing with complex quantities, and that's why you need to become very comfortable with Appendix B material. We'll start then with an example that we could have gone through yesterday, but we ran out of time. Let's look at now going the opposite direction. Let's say that we are in the frequency domain and we have a phasor collection of quantities, and we want to take that into the time domain. Yesterday, I think we finished with going from time domain into a phasor form. We want to start today going the other direction, and then we'll see how we can translate or go between time domain and frequency domain. And the reason we're doing that, again, is to try to simplify our life. Instead of differentiating in the time domain, if we're in sinusoidal steady state, that's equivalent to multiplying by j omega. If we integrate, we do the reciprocal or the inverse operation. Integration in the time domain transforms in the frequency domain to division by j omega, or multiplication by 1 over j omega. Then we will derive, well, in the process of working through a circuit illustrating this, we will derive these relationships for impedances. We'll see that the resistors they don't really care what domain they're in. There always are. They're constant. They don't, remember, they don't have an Eli or an ice. They have ohms. So they now have Ohm's law, and that just says that current and voltage are directly a constant relationship apart. Their peaks and valleys are always aligned. They're in phase, the voltage and current on a resistor. Not so for inductors and capacitors, because they have these differential relationships relating current and voltage, the Eli and ice that we've been using. And because of that, an inductor's impedance depends on the frequency, and it's complex. It's j omega L. The impedance of a capacitor in a sinusoidal steady state analysis is 1 over j omega c. You have to know what's on the side, what is our frequency, what's the omega, and then you give me the parameter value, L or C, and I can tell you, or you can compute, the impedance associated with that device or that circuit element. Let's then get started going between domains, going between time domain and frequency domain. Here we will actually go from phasor to sinusoid in the time domain. So this phasor is the frequency domain. And we want to now find the time domain waveform corresponding to some phasor, where the phasor V bar is now given in this inside the brackets. And in fact, this particular bracketed expression is a combination of sinusoids. We have one piece here and another piece there, and we need to combine those. And are they in a form that is convenient for combining? If you have your protractor and straight edge and ruler, yes, you can combine these because you could sketch these. You can say, oh, I'm going 60 in the real direction and then up 30 in the vertical direction. And the other one is, oh, I have to go away from the origin or from that head of the phasor. You could add these vectorially. You could say, oh, now that I'm at this location, now go in the direction of 100 at an angle of minus 28, and wherever all of those heads and tails take you, then wherever you started to the final head is your resultant amplitude and angle. Here, though, it might be easier, if we're doing this analytically, is to go ahead and convert one to another form that will make it easier to combine. This one is in rectangular form, and this one is in exponential or polar or phasor form. And if we're combining complex numbers, which one is maybe cleaner to convert to combine? Usually when you're adding and subtracting, you want things in the rectangular form so that you can just add components. That means let's convert the polar. We simply keep the rectangular form as given. And now to convert from polar to rectangular, we just say, oh, project 100, that length, onto the real line through this angle, minus 28 degrees, and project the 100 length onto the vertical through this angle of minus 28 degrees. Or we now have 100 cosine of minus 28 degrees, and we are now going vertical, so we have to keep track of what's horizontal and what's vertical, plus j 100 sine of minus 28 degrees. And what do you expect to see coming out of 100 cosine of minus 28? What range of a number? What's the cosine? And now just kind of keep track of cosine being an even function and sine being an odd function. Cosine of minus 28 is the same as cosine of plus 28. I'm seeing this, but I don't know if you're seeing what I'm seeing. So let's make it clear. We're now down here at 28 degrees, and we want to project this onto the real line. It doesn't really matter that we're down below the real line or above by that same amount. The projection is going to be the same value. And what is that value going to be? I like to sort of keep track of what's the halfway angle, 45 degrees, and I know the cosine of 45 degrees is 0.707. 28 is not quite 45, so the cosine is going to actually be larger than 0.707 times 100, or bigger than 70. So when I get a number, I better be seeing a number bigger than 70, is what I'm thinking. Or if you do the cosine, and now you're going, just plug it into your calculator. Sometimes you make a mistake, so I'm just trying to give you ways to catch those mistakes before you get too far into the solution. Here, this ends up being 88.29, and for a similar argument, sine of 45 is 0.7. Now we have sine of an angle that's less than 45, so that's going to be smaller than 70, and sine is an odd function. That's now minus j, and the value this one ends up being is 46.95, which is less than 70. And we can combine those, and we have 148 combining the real components and the imaginary components. And again, you can draw the answer in the back of the book. If these are now tick marks of 50, we're at 150 roughly and down about a third of 50. So we're about there with our protractor and straight edge. That's what we should be getting if we now convert this to its polar form. This is the phasor form of a combination of two complex numbers. This was 150 for real, and here is our imaginary, and we went down about 1/3 of 50. That's where that was coming from. And this now we can say, oh, we just need to find the hypotenuse, or the length of that phasor. That's 148.29 squared plus the imaginary part squared. And the angle, don't forget the quadrant. Now we are going down 16.95. There's where the negative is, because your calculator may not keep track of what's upstairs and what's downstairs when you're doing an inverse tangent, depending on your calculator. And this is now 148.29. That's why sometimes it's helpful to draw these pictures to guide your final answer. Or this ends up being 149.26 at an angle of minus 6.52 degrees in volts. That's in the frequency domain. Wow, I was writing bigger the other day. So if we now put that into the time domain, we simply remember what was on the side. In this case, I didn't give you an omega. I just said here's the magnitude and angle, or the rectangular representation of that original complex combination. We would have to be told what are we moving at, what are we oscillating at, what's the omega. But if we don't know, we just say, oh, it's cosine omega t. The phase is minus 6.5 degrees and the amplitude is 149. That's how we could then convert from the frequency domain or phasor back into the time domain. And if you were given this cosine waveform in the time domain, you can immediately pull that into the frequency domain by saying, oh, that's 149 at an angle of minus 6.52. You need to be comfortable going back and forth. If that's the case, let's now derive this relationship. The relationship between time domain differentiation and what that corresponds to in terms of an operation in the frequency domain. We're going to show that that's equivalent in the frequency domain to multiplication by j omega. And obviously that differentiation depends on the frequency, omega. That's why we have this j omega. Let's get started with that. So let's assume we have a voltage or a signal v of t expressed in the time domain as a magnitude cosine omega t, the radian frequency is omega, and the phase is theta. We know that that's the real component of this complex exponential expression. We can then say, oh, that's equal to the real part of v sub m, the magnitude, e to the j argument of that cosine, omega t plus theta. We can now say, oh, we know our exponential properties, or the properties of exponents. We can now factor that into two pieces, and we can now hopefully see we have a time invariant piece, or a piece that's not a function of time right there, a magnitude at an angle, and our rotating phasor, e to the j omega t. Or let's now just write that as a v sub m bar, e to the j omega t. That's now a way to translate this time domain cosine into the frequency domain. We now have it as this rotating phasor with a gain in front of that rotating phasor, or this adjustment of v sub m bar. And v sub m bar says, oh, at time 0 you just have an angular offset, and v sub m's magnitude gives you the distance that phasor is, or the length of that phasor that's rotating around in the complex plane. Let's differentiate. If we differentiate the time domain waveform that we started with, which was v sub m cosine omega t plus theta, now you either memorize this, or you look it up, or you ask somebody, Siri, what's the derivative of cosine? You might have fun finding out what you hear from the experts behind the ask, huh? What's the one? Nah, I've forgotten, so I'm not even going to go there. But there's now our derivative of cosine. Minus omega v sub m sine omega t plus theta. But we're playing with cosines. How are cosine and sine related? If I now want to convert that to a cosine so that I can compare it at the bottom with what I started with, which was this, real v sub m e to the j omega t. That's my beginning waveform. How do I convert, or how are sine and cosine related as waveforms? Sine is 90 degrees behind cosine. So now we can say, oh, this is omega t plus theta minus 90 degrees. And we can move that negative sign inside the argument by adding or subtracting 180. Let's try to make the sum of all of those angles small, so we'll add 180. We can now say this is omega v sub m cosine omega t plus theta minus 90 degrees plus 180 degrees. That's just accounting for that negative sign or eliminating it out front. We've now moved it inside the argument of our cosine. Let's combine those angles. And to get this in a form that we can compare with, which is now in the complex exponential form, let's now write this as a complex exponential. This is now equal to the real component of omega v sub m, and now what? The complex exponential just possesses that same argument in its exponent. We now have e to the j omega t plus theta plus 90 degrees. Trying to make sure each step is clear how we're getting between one and the other. And now let's factor that out. We're trying to end up with something that looks like what we started with. So let's now separate all of those complex exponentials. One of those is this e to the j theta. Another one, maybe I should have written that first, but we also have e to the j 90 degrees, and we have e to the j omega t. We've now isolated the rotating phasor piece. Let's now combine or collapse that into the phasor form. That's v sub m bar. That's just v sub m at an angle theta. And what's e to the j 90? Can we rewrite e to the j 90? Or what is e to the j 90? If this is our complex plane, here's the real part, here's the imaginary part. They gave me a hard time last week. We were playing a game in 320. Pin the magnitude plot on the frequency axis. Now we're actually trying to pin that point, e to the j 90 degrees, on the complex plane. Where is it? Where is that point? If you had to identify that point, if somebody said, oh, walk to e to the j 90 degrees, you're going to go, no problem whatsoever. I've had ECE 220. So where do you go? They've now told us where to go. They've said EJ90. Go to EJ90. What's the magnitude? How far are we going to have to walk? Is it going to be a trek? What's the magnitude of e to the j 90? What's the magnitude of e to the jx? Don't tell me you've forgotten the joke. Euler and the joke. E to the jx is cosine x plus j sine x. Magnitude of that. There's our joke. Cosine squared x plus sine squared x is 1. The magnitude of e to the j 90 degrees is 1. So we don't have to walk very far. And how are we getting there? At an angle of 90 degrees. Now do you know where we're at in the complex plane? We are now right there. We are at J, or if we wanted to express it in terms of angles, it's e to the j 90 degrees. That's the same location. All of that, Euler and joke, so that we can rewrite that as a j. But that's going to become quite common. But when you see j, if it's confusing, sometimes maybe you want to put it in that exponential angular form, e to the j 90. But now what do we have? Now we can rewrite this and say, oh, this is the real of j omega v sub m bar, which is what that was, e to the j omega t. Can I erase? And we want to compare this expression with that expression. This is now right here. How has it been changed? We differentiated. That's what gave us this start right here. We differentiated in the time domain, and we said, oh, we end up with this. We want to compare this expression with that expression. What's different? Now we are multiplying by j omega. We differentiated in the time domain, and in the frequency domain, which is where we're living inside the real brackets, now we're in the frequency domain. Oh, that's equivalent. Since we're in sinusoidal steady state, we're playing with sines and cosines. That's equivalent to multiplication by j omega. Hence, if somebody gives you in the time domain v of t and they say, oh, its phasor form is capital V sub m bar, then if they say, oh, I'm differentiating in the time domain, you go, well, I'm over in the phase domain. Then all you have to do is multiply by j omega and work in the phase in the frequency domain. You may not believe me, but that's going to make your life easier. Now you'll just be able to do algebra with complex numbers instead of calculus with derivatives and integrals. Differentiation in the time domain corresponds to or transforms into multiplication by j omega. This is when we're in sinusoidal steady state. In the follow-on class, we'll find that we are going to generalize j omega even. We'll call it an S. And it will have, not only will we be on the imaginary axis, but we'll be in our entire complex plane. It will have a real component and an imaginary component. In the sinusoidal steady state, we're just living on the imaginary axis with j omega. More than you wanted to know. Let's look at integration. Here's our fact from calculus. If we integrate cosine omega t plus theta, that's equal to 1 over omega sine omega t plus theta. And if you really wanted to just play around, you could put all of those into complex exponentials and integrate the exponentials. Those are usually easier to integrate than sines and cosines, and you can rederive all of these relationships. We can now rewrite that integration in terms of cosine by just remembering the trigonometric relationship or the relationship in the time domain of sine and cosine. The sine lags, and another way of thinking of that would be, oh, here's our graphical tool that we said we might use. Now the sine is behind or lagging the cosine by 90 degrees. If you wanted to combine sines and cosines at the same frequency, you would put the cosine magnitude and angle relative to the positive cosine axis, the sine on the sine axis, and then do the vectorial combination to obtain a single cosine waveform. Now what do we want to do? Don't answer that. Close the door, please. No, everybody was walking out. I said, now what do we want to do? And I said, everybody's leaving. But you didn't. Thank you. You deserve a round of applause. We want to now go into the frequency domain. We're in the time domain. Let's now write this in the frequency domain. What do I need to put inside the curly braces? I have 1 over omega. Then I simply need to put this in an exponential, complex exponential form. That's e to the j, and my exponent is just the argument of the cosine. And you know the drill. Let's now break apart e to the j into its various parts. And now we could say, oh, this is now e to the j minus 90 degrees, e to the j omega t plus theta. Do we need to walk again on our e to the minus j 90 degrees, or do you know where that is? We could think of this many different ways. You could say, well, I know what e to the j 90 is. Well, you're just taking it, you're just dividing by e to the j 90. What was e to the j 90? Or you can now say, oh, this is 1 over e to the j 90. Or if you really were walking, you could say, oh, I just need to go the distance of e to the j minus 90, which I know is 1. I know the joke. So you're going 1, and then you're going a minus 90. So now you're at 1 over j to replace this. Or we now have the real of 1 over j omega times e to the j omega t plus theta. Which, if we compared this with what we started with somewhere, we didn't really start with it, but we started with this in the time domain, which in the frequency domain was e to the j omega t plus theta. That's what we started with, and now what did we end up with? 1 over j omega, scaling that. And in the time domain, we were simply integrating. In the frequency domain, we now can say, oh, we have simply multiplied by this factor 1 over j omega. If you now had this integral differential equation involving some time domain sinusoid, you could move that whole mess into the frequency domain. By anywhere you see an integral, you divide by j omega. Anywhere you see a derivative, you multiply by j omega. And you replace that sinusoid with its phasor representation. Let's do that. Let's now look at, so here's the summary. If you start with V, and its phasor form is now capital V sub m in the time domain, so here's the time domain. Here's the frequency domain. As electrical and computer engineers, you have to get comfortable thinking in both domains, time domain and frequency domain. Now, I want to find the sinusoidal steady state current in this RLC circuit. We're going to work it kind of the long way to begin with, but in the process we're going to actually see some relationships for the impedances of the inductor and capacitor. The SS means sinusoidal steady state. We've assumed transients have disappeared, and we've been hitting this circuit with a sinusoid, little v of t. What's the frequency of that sinusoid? How fast are we shaking? 2 radians per second. And if you needed to, you could say, oh, that's 2 pi f to find your frequency in hertz. We now know how we're moving, how we're oscillating, and every waveform, every voltage, and every current in this linear circuit is shaking or vibrating at 2 radians per second. So we should expect I sub steady state to be oscillating at 2. So that's on the side. We know that that's our frequency that we're moving with. Let's now say that we are wanting to simply write a KVL equation in the time domain. Can you write such an equation? And here I'm not going to write that sinusoid completely. I'm just going to say that's v of t. Well, we can just walk that around that mesh. We now are seeing a voltage rise and not a drop on v of t. So that's a minus v of t. Then we have, with the passive sign convention, a voltage drop on that resistor. That's 4 I of t. Plus may I just call that an L for now? I need the voltage dropped across that inductor. That's now Eli, or L di dt. And we could say, and then the voltage dropped across that capacitor. That's a state variable. But let's convert all of these into currents now. And how can I relate current and voltage? Through ice on my capacitor. I now know that I sub c of t is c dv sub c dt. I want to solve that for v sub c. Or if I now integrate both sides, and my I sub c in this case is, in fact, since it's in series, it's the same current as the current through the resistor and the inductor. Or I've now rewritten this as minus v of t plus 4I of t plus L di dt plus 1 over c integral I of, let's say, tau d tau, and that's equal to 0. We're in a steady state, so we're not even going to really worry about the limits of that integral. This is just now, we're shaking together. We're done in the time domain. Can you now push us into the frequency domain? This is now a integral differential equation. I want to do some algebra. So we say, well, we know how to convert a derivative into the frequency domain. We know how to convert an integral into the frequency domain, and they're all operating on the same current. And we know what v of t is in its phasor form. Let's then go into the frequency domain. How do I rewrite minus v of t in the time domain in the frequency domain? 50 at an angle of 75 degrees. And we need to make sure that we have the minus sign, so I now have minus, what did I say, 50 at an angle of 75 degrees. Plus R times the phasor form of that time domain current, little I of t. That I'm just going to say is capital I bar. Plus, now what do I do? L is not a function of time, but how do I write di dt in the time domain? How do I transform that into its equivalent form in the frequency domain? We just derived that relationship. Now we multiply by j omega, and that's now what we have as its equivalent representation in the sinusoidal steady state in the phasor domain. That's now L j omega I bar. If we do the same thing with the integral, we now divide by or multiply by 1 over j omega I bar, and all of that is equal to 0. Now we're in the frequency domain, and we have one unknown quantity. That's this current phasor I bar. Let's factor out all the terms that are scaling I bar. We now have R plus j omega L plus 1 over j omega C I bar is equal to 50 at an angle of 75 degrees. And this was really just our supply voltage V bar. I now have Ohm's law in the frequency domain. I have a resistance, but now we'll generalize that to an impedance. Z times current is equal to voltage. Z is equal to, Zi equals V. This is now our impedance. And it's our total impedance. We could just say that's Z sub t. Or Z sub t now is R plus j omega L plus 1 over j omega C. And what we can now do is we can actually generalize from this first example. This is the resistor's impedance. Let me write it as resistor's impedance. This j omega L is what, if we see an inductor in our circuit, if we take that circuit into the frequency domain, we replace that inductor with j omega L, and that's now its impedance. This is now the inductor impedance. And this term is now the impedance of the capacitor. And we have those numerical values. The resistor was 4. On the side, we had our frequency, which was 2. And L in this example was 3. Plus 1 over J 2 times, and C in this case was 1/8. Now our impedance is just a complex number. Z total is now 4 plus J 6, and now we have 1 over J over 4, or this is now, and the J downstairs, what's that look like upstairs? Or we can multiply by J over J. We get a -1. This is now minus J4. That's our capacitor. So when you see Inductors' impedances, those are positive. Capacitors' impedances are minus something. We combine those in series, and now we have 4 plus J2. We had this Z sub t times I was equal to 50 at an angle of 75 degrees. We now can say, oh, I bar is just 50 at an angle of 75 degrees divided by that total impedance. How do we do that? You could say, well, plug it into your calculator. Maybe. Or you could rationalize the denominator, multiply by the conjugate of 4 plus J2, which is 4 minus J2. Or you could convert 4 plus J2, it's now in rectangular form, you could convert it to polar form, and then you just have to divide the magnitudes and subtract angles. Let's do it that way. So now we could say, oh, I bar is 50 at 75 degrees divided by the magnitude of that is the hypotenuse of the right triangle, the square root of 4 squared plus 2 squared, which ends up being the square root of 20, at an angle. What would you guess that angle to be? Positive or negative? Do you see the angle in the complex plane? Can you draw it? You're walking over 4 paces in the real direction and up 2 in the vertical. Do you see the angle? Am I bigger than 45 or less than 45? Less than 45, and I'm what? Bigger than 4 away from the origin. I'm actually the square root of 20 from the origin. The angle is the inverse tangent of 2 over 4. That ends up being 26.56 degrees. And numerically, the square root of 20 is a little less than 5 and a little bigger than 4. That ends up being 4.472. I divide 50 by 4.5, and I end up with 11.18. I subtract 26.5 from 75, and I end up with 48.43 degrees. That's the frequency domain answer. Somebody now gets impatient and they say, well, I don't care what you're doing in the frequency domain, you crazy ECE majors. Get me back in the time domain. I want to see this. I want to see this waveform. Can you now provide them with an answer? What is little I? And now this is sinusoidal steady state. The transient has vanished. We're now just sitting there shaking. With what magnitude? And it's a cosine. How fast are we shaking? That was on the side. That was our 2. And then we have an angle or an offset, a phase shift. And now you can report back without having to solve this differential equation, integral differential equation. We now just moved into the frequency domain. We replaced the impedance or the inductor with its equivalent impedance, j omega L. We effectively replaced the capacitor with its impedance, 1 over j omega C, and we just did KVL with complex numbers, and we ended up with this sinusoidal steady state current in this series RLC circuit. Now we've moved from chapter 8 into chapter 9. This is now sinusoidal excitation and sinusoidal response versus constant excitations in chapter 8. We'll pick up with more of this analysis in the frequency domain tomorrow.